Really fundamental question.
Mm.
Is the electron actually fundamental?
Mm.
Is it just a single indivisible point like the standard model says? Or could there be something inside, like how we found atoms weren't the end of the story?
Exactly. It's that classic progression in physics, isn't it? Atoms, then the nucleus and electrons, then quarks inside protons and neutrons. It makes you wonder, what about the electron itself?
Right. So we've really dug into a lot of material here, experimental results from particle colliders, these super precise measurements, and then, well, the more theoretical ideas like preons or string theory.
A real mix.
Yeah. And our mission today is pretty clear. Is there any solid evidence that the electron isn't this simple point-like particle we think it is?
Okay, so let's start with that word fundamental. What does it really mean when particle physicists say that?
Okay, so fundamentally, it means it's not made of anything smaller. It's a basic building block, right? And the standard model, our best current theory of, well, everything at that scale, lists the electron as one of these fundamental particles. It's a lepton.
And it has those key properties we learn about: mass, negative charge, spin 1/2.
And that specific quantum number, the electron-lepton number.
Right. And crucially, the standard model describes it as a point-like Dirac fermion. Now, Dirac fermion is just physicist speak for a fundamental particle with spin 12 that follows certain rules.
Quantum mechanics, special relativity.
Exactly. But the point-like part is key for this discussion. 0 size, no spatial extent.
And that idea that it has 0 size is absolutely central to quantum electrodynamics, QED.
Oh, completely. QED is this incredibly successful theory describing how electrons and photons interact, and its predictions rely heavily on the electron being point-like. Those predictions, they've been tested to just astonishing precision.
Unbelievable precision. And so far, every experiment, every time we've looked closer using higher energies.
Like turning up the magnification on our microscope.
Exactly. The electron just keeps acting like a point. We haven't seen anything to suggest it has parts.
Which implies, well, if there is some kind of substructure, it must be hidden at energy scales way, way beyond what we can currently probe.
Interesting point, too. The standard model itself doesn't actually predict any structure.
Yeah.
No excited states either.
Right. Which often leads to the question, what about the heavier leptons, the muon and the tau? Could they just be, heavier excited versions of the electron?
It feels intuitive, doesn't it?
Yeah.
But no, the standard model treats them as separate fundamental particles, different generations.
And there are good reasons for that. Matt Strassler, for instance, makes the point that if they were just excited electrons, you'd expect a whole bunch of related particles with different spins around the same mass.
Which we just don't see.
You don't see them. Plus, the way they decay, it doesn't fit the picture of simply dropping down from an excited state of one particle. It points to them being distinct things.
Okay, so the standard model picture is clear. Point-like, fundamental. But science is about checking, right? So how do we actually try to look inside?
Well, the main way is high-energy scattering. Basically, you smash things into the electron or smash electrons into other things at really high speeds.
Firing tiny bullets, essentially.
Kinda, yeah. The more energy you use, the finer the detail you can resolve. We talk about momentum transfer, Q squared, as a measure of this. Higher Q squared means you're probing smaller distances.
It's like a sharper lens.
Precisely. And how the electron scatters tells us about its electromagnetic properties, which we describe using things called form factors, F1 and F2 of Q squared.
Right, these describe how its charge and magnetism appear to be distributed when you probe it.
Yeah, and for a perfect point-like Dirac particle, theory says F1 should just be 1 and F2 should be 0. Simple.
But it's not quite that simple because of quantum mechanics, right? QED corrections.
Exactly. QED introduces tiny quantum effects radiative corrections that slightly change those values. That's actually where the electron's anomalous magnetic moment comes from, this slight deviation from the simple picture.
And the amazing thing is, when we do the experiments, electron scattering, electron muon, even looking at the electron vertex and electron-proton scattering,
all these different angles,
the results match the QED predictions for a point particle, including those tiny quantum corrections, incredibly well. We don't see any extra Q squared dependence that would shout, hey, I have size, beyond what QED already accounts for.
Which is a huge contrast to something like the proton.
Oh, yeah. The proton's form factors change dramatically with Q squared.
They drop off quickly. And that's direct, undeniable evidence that the proton isn't point-like. It has a finite size, it has quarks inside. We can even measure the proton's radius from how those form factors change.
But we can't do the same thing for the electron. There's no equivalent electron radius measurement from scattering in the same way.
Nope. Because the form factors, once you account for the known QED effects, are basically constant. There's no slope at q squared equals 0 to measure a radius from. So instead, experiments just set upper limits.
They say, well, if it does have a size, it has to be smaller than this.
Exactly. Which, by the way, is super useful. The fact that the electron behaves so predictably as a point particle makes it a fantastic tool for probing other things like the proton. Imagine trying to figure out proton structure if your probe, the electron, was also some complicated blob.
Yeah, that would be a nightmare. So what kind of limits are we talking about? How small is small here?
Well, direct scattering experiments, like those at the LEP collider, push the limit down below about 10 to the minus 18 liters. Pretty tiny.
Extremely tiny.
But then you get even tighter limits from indirect methods, combining the ultra-precise G-2 measurements with certain models, like the Brodsky-Drell model.
We'll get to G2 in a bit.
Right. That pushes the implied limit down even further, maybe below 10 to the minus 22 meters, depending on assumptions. And then there's another approach, looking for contact interactions.
Contact interactions. Okay, what's that about? Sounds like touching.
Sort of. The idea is if the electron is made of small bits, let's call them preons for now, then maybe at really high energies, those bits could interact directly with the bits inside another particle.
Okay. A new kind of interaction, not in the standard model.
Exactly. It would be a sign of physics happening at some very high energy scale, the compositeness scale, usually called lambda. But even at energies below lambda, this new physics could show up as an effective short-range interaction between electrons and other particles. Looks like they just touch, hence contact interaction.
So we'd look for experiments where particles seem to interact slightly differently or more often than the standard model predicts.
Precisely. You look for deviations. At electron-positron colliders, like LEP, they looked at things like electrons and positrons annihilating to produce other particle pairs. At hadron colliders, like the LHC, they look in processes like Drell-Yan quark-antiquark making lepton pairs or just producing high-energy jets.
And did they find any unexpected touching?
Nope. Nothing significant has shown up. The standard model predictions hold up remarkably well.
Which means?
Which means we can set very high, lower limits on this compositeness scale, lambda. If these interactions exist, the scale associated with them has to be really high.
How high are we talking?
For interactions involving just electrons, LEP data push lambda above maybe 8 to 10 TeV tera-electron volts.
Okay, that's a serious energy scale.
It is. And for interactions involving electrons and quarks, the LHC experiments, ATLS and CMS, have pushed those limits much higher, into the 25 to 36 TeV range, depending on the specific interaction. Same goes for general lepton-quark interactions. The particle data group summarizes these consistently very high limits.
Wow. So if there are smaller bits inside, they're bound together incredibly tightly, requiring huge energies to see any effect.
That's the message. And the consistency across different types of searches and different experiments really strengthens the case against compositeness at the energy scales we can currently access.
Okay, so scattering looks point-like. Contact interactions aren't showing up.
Okay.
What about excited electrons, like excited atoms?
Yeah, that's another classic sign of compositeness you might expect. If the electron has internal parts, maybe it can rearrange itself into higher energy states, like an atom can. We call these hypothetical states excited electrons, or E-star.
So it would be like an electron, same charge, same spin, but just heavier.
Exactly. Heavier and unstable. It would quickly decay back down to a regular electron, probably by spitting out a photon or maybe a Z or W boson.
Okay, so experiments will look for those decay products. An electron plus a photon, or an electron plus a Z appearing together.
That's the signature. E going to E gamma is a common one, or E to EZ, or even E to neutrino W experiments at LEP, each or R, and definitely the LHC have searched hard for these kinds of signals.
And any E-stars turning out.
Again, null results so far, no confirmed sightings. What we have are limits on how massive these E-stars could be and how strongly they might interact.
What kind of mass limits are we talking now?
Well, LEP set limits up to around 100 GeV or so for pair production and indirectly higher. HERA had limits depending on couplings, but the LHC has really pushed the frontier. CMS and ATLS have excluded E-stars up to masses of around 5 TeV, even a bit higher in some analyses.
5 tera-electron volts. That's massive for a fundamental particle's excited state.
It is, though these limits do depend on assumptions about how the E-star is produced and how strongly it couples, that lambda scale again.
Sure, caveats apply, but still, No sign of them up to multi-DV scales.
Right. When you combine that with the arguments we already discussed about why the muon and tau aren't just excited electrons, it really puts the squeeze on simple atomic-like models of the electron.
Meaning?
Meaning, if the electron was like a tiny atom, you'd probably expect to see excited states relatively easily. The fact that we don't, up to such high masses, suggests that if there are constituents, they are bound together extremely tightly with a huge energy gap before you get to any excited configuration.
Okay, so the direct searches, scattering, contact interactions, excited states all come up empty. What about the indirect route, those ultra-precise measurements?
Absolutely. This is where things get arguably even more constraining. The prime example is the electron's anomalous magnetic dipole moment, G-2, G2.
Right, you mentioned this gives limits on the radius.
It does, but it's more fundamental than that. Measuring G2 is one of the most stunning triumphs of QED and experimental physics.
Why is that?
Because the theoretical prediction from QED and the experimental measurement agree to an absolutely staggering degree. We're talking agreement to something like 10 or more significant figures, part per trillion precision.
Okay, that is difficult to even comprehend. How does that constrain substructure?
Well, think about it. If the electron had bits inside, those bits and the forces binding them would inevitably contribute tiny quantum loop effects to the magnetic moment.
Ah, they'd add extra wiggles to the calculation.
Exactly. And those extra wiggles would almost certainly spoil that beautiful agreement between theory and experiment. The fact that the agreement is so good puts incredibly tight limits on any new physics that could affect the electron's magnetic moment, including substructure. It's like saying the electron follows the QED rulebook almost perfectly, leaving very, very little room for any hidden chapters about internal parts.
It's like measuring the distance to the moon and being off by less than a hair's width, that kind of analogy.
That's the kind of level we're talking about. It's mind-bending. And yes, models like the Brodsky-Drell one try to quantify this. They relate potential tiny deviations in G2 to the mass and size of hypothetical constituents. Given the agreement, these models imply constituent masses must be huge, TeV scale or higher, and the effective radius incredibly small, like we said, maybe 10 and 40 meters or less, even tighter than some direct search limits.
It's amazing that measuring this one property tells us so much.
And contrast it with the proton and neutron. They have large anomalous magnetic moments.
Because they're composites.
Exactly. Their G2 values are dominated by their quark structure and the strong force. The electron's G2 being so close to the simple Dirac value is a massive piece of evidence for its elementarity.
And we should probably mention the muon G2 situation briefly.
Yeah, it's relevant. There is a small but persistent tension between the measured value of the muon's G2 and the standard model prediction.
An anomaly.
A potential anomaly, yes. It's being intensely investigated. But the very fact that we see this tension for the muon, while the electron's G2 agrees so perfectly, actually reinforces the electron result. It also hints that whatever new physics might be causing the muon discrepancy, if it's real, might be specific to muons or affect different lepton generations differently. It doesn't seem to be a generic all leptons are composite effect based on the electron's data.
Okay, G2 is incredibly constraining. What about the electron's electric dipole moment, the EDM?
Another super precise probe, an EDM measures a separation of charge along the particle's spin axis. Think of it like the particle being slightly more positive on one end and slightly more negative on the other.
Which would be weird for a fundamental particle.
Very weird. It would violate fundamental symmetries, time reversal, T, and charge parity, CP symmetry. The standard model actually predicts a tiny, tiny non-zero electron EDM, but it's incredibly small, something like 10 all-electron centimeters, way too small for us to measure currently.
But the experiments looking for it have set much stronger limits than that, right?
Oh, vastly stronger. Experiments like ACME2 and others at JLA have pushed the upper limit down to around 10 U or even 10 U agrisometers.
So orders of magnitude more sensitive than the standard model prediction.
Many, many orders of magnitude. This makes the electron EDM an incredibly sensitive hunting ground for physics beyond the standard model, because many BSM theories do predict new sources of CP violation that could generate a much larger EDM, potentially within reach of these experiments.
Okay, so it constrains BSM theories. How does it constrain electron substructure?
Indirectly. If the electron were made of constituents, interactions between those constituents could easily introduce new ways for CP symmetry to be violated beyond what the standard model allows for an elementary electron.
Ah, so the internal dynamics could generate an EDM.
Potentially, yes. So a composite electron might naturally be expected to have a larger EDM than the minuscule standard model prediction. The fact that experiments see nothing, that the limit is so incredibly tight, puts severe constraints on any composite model. The model would have to somehow explain why these internal interactions don't generate a measurable EDM, which can be quite challenging.
Okay, so experimentally, the case for a point-like electron looks pretty solid.
Extremely solid based on current data.
Yet theorists haven't stopped thinking about alternatives. Why explore these ideas if the evidence isn't there?
Well, partly it's about pushing boundaries, asking what if, but mostly it's driven by known issues within the standard model itself. Things it doesn't explain, like why are there 3 generations of particles? Why do they have the masses they do? What about gravity? So people explore models that might address these issues, and sometimes those models involve particle compositeness.
Like the Preon models you mentioned earlier, building blocks of the building block.
Exactly. That was an early, quite intuitive idea. Maybe the quarks and leptons we see aren't the bottom layer. Maybe they're made of even simpler things, preons.
And the motivation was to simplify the particle zoo.
That was a big part of it. Reduce the number of fundamental entities. Maybe explain the repeating patterns, the families or generations. Perhaps even explain charge quantization or provide a different way to break electroweak symmetry without a fundamental Higgs boson.
And the picture was these preons bound by a new, super strong force, hypercolor.
That was the typical setup. A new force analogous to the strong force binding quarks, but acting at a much smaller scale, binding preons into quarks and leptons. The Harari-Shupin model was one well-known example trying to do this with just a couple of basic preons.
But these models ran into trouble, didn't they?
Big trouble. The main one was the mass paradox. If you confine these preons into the tiny volume implied by the electron's apparent size, the uncertainty principle says they must have huge momentum and thus huge energy.
So the constituents would be much heavier than the electron itself.
Exactly. Which means you need an absolutely enormous binding energy, almost perfectly canceling out the constituent mass energy to end up with a light electron. That requires incredible fine-tuning, which physicists generally don't like.
Plus, no experimental evidence for preons or hypercolor.
None whatsoever. And many simple preon models also struggle to reproduce the precise predictions of the standard model, like that G2 value we talked about. So between the theoretical challenges and the lack of experimental support, plus the success of the standard model and other ideas like supersymmetry or string theory, interest in preons has really faded over the years.
Okay, so preons didn't quite pan out. What about string theory? That's a very different beast.
Totally different paradigm. String theory doesn't propose smaller point-like particles inside the electron. It says the fundamental entities aren't points at all, but tiny, vibrating, one-dimensional strings.
And the electron is just one way a string can vibrate.
Essentially, yes. Different particles correspond to different vibrational modes of these fundamental strings. An electron is one pattern, a photon is another, a quark is another.
So in string theory, does the electron have a size?
Its effective size would be related to the characteristic length scale of the string itself, which is usually assumed to be around the Planck length.
Which is
unimaginably tiny, around 10 to the minus 35 meters. That's orders and orders of magnitude smaller than anything we can probe experimentally now or likely ever directly.
So string theory offers a kind of substructure, but it's not really compositeness in the way preon models meant it. And it's way beyond testable limits for now.
Right. String theory aims to be a theory of everything, unifying quantum mechanics and gravity, but direct experimental proof that electrons are tiny vibrating strings is currently lacking. It's a very compelling mathematical framework, but connecting it definitively to experiment at these scales is tough.
Okay, what about Technicolor and similar ideas? Weren't they about compositeness too?
Well, the original goal of Technicolor wasn't primarily electron compositeness. It was about finding an alternative to the Higgs mechanism for explaining particle masses.
Right, dynamical electroweak symmetry breaking.
Exactly. It proposed a new, strong force, like QCD but stronger, acting on new fermions called technofermions. Their condensation would break the symmetry and give mass to the W and Z bosons.
But did that imply electrons were a composite?
Not directly in the simplest models. But to give masses to the ordinary fermions, like electrons and quarks, you usually needed extensions like extended Technicolor or ETC.
And that's where compositeness might creep in.
Potentially. ETC involved interactions linking standard fermions to technofermions. This could either imply some level of compositeness for the standard fermions, or at least generate effects that look like compositeness, such as contact interactions. Some specific models, like one by Civukala and others, explicitly proposed a composite Technicolor standard model and predicted a compositeness scale around 1 to 2.5 TeV.
Which is actually within the range of the LHC probes.
It was, yeah, which
Yeah.
made it testable.
Like Technicolor hasn't really taken off either, has it?
It faced significant hurdles. Precision electroweak measurements were hard to satisfy, avoiding problematic flavor-changing neutral currents was tricky, and crucially, the discovery of the Higgs boson at the LHC.
Which looked pretty standard model-like.
Exactly. It looked quite like the relatively simple, fundamental scalar particle predicted by the standard model, not like the composite states typically expected in Technicolor scenarios. While some ideas about composite Higgs models are still being explored.
Where the Higgs itself is made of something else.
Right. But direct applications for lepton compositeness in those viable models are often less prominent, and they still face all the strong experimental constraints from the LHC on contact interactions and excited particles that we've already discussed.
Okay, so let's pull all this together. We looked at scattering, contact interactions, excited states, precision measurements like G2 and EDM, and theoretical ideas like preons, strings, Technicolor. What's the bottom line?
The overwhelming consensus, really driven by the data, is that the electron behaves exactly like an elementary point-like particle down to the smallest distances we can currently probe. That's roughly 10 UR to 10 Uring meters, corresponding to energy scales in the multi-TeV range.
And all the different types of evidence point the same way.
Pretty much. The form factors are consistent with a point particle plus QED corrections. The limits on contact interactions push any compositeness scale very high. We haven't seen any excited electrons despite looking up to TeV masses. The G2 agreement is phenomenal. The EDM is incredibly small. And we have good arguments why muons and tachys aren't just excited electrons. It's a very consistent picture.
And just to be clear, there are no lingering, unexplained experimental results directly related to the electron itself that hint at structure. We hear about anomalies sometimes.
Not really any that point strongly and directly to electron substructure. The muon G2 thing is the most prominent lepton anomaly, but as we said, the electron seems fine. You sometimes see weird effects in condensed matter physics, fractional charges in the quantum Hall effect, things like that.
Right, I've heard of those.
But those are understood as emergent phenomena. It's about the collective behavior of many electrons interacting within a specific material environment. It doesn't mean the individual electrons themselves are composite or breaking apart. It's a property of the system, not the particle.
Okay, important distinction. But let's play devil's advocate. If someday we did find evidence for electron substructure, what would that mean?
Oh, it would be absolutely revolutionary, a complete paradigm shift.
Bigger than discovering quarks.
Arguably, yes, because quarks were postulated to explain hadron properties, but leptons were considered truly fundamental. Finding structure in the electron would mean the standard model is definitely just an effective theory, a low-energy approximation of something deeper.
We'd need new particles, new forces.
New fundamental constituents, a new binding force. And it could potentially unlock explanations for some of the standard model's biggest mysteries. Why 3 generations? Why the specific masses and charges? Maybe even the nature of the fundamental forces themselves could turn out to be emergent properties of this deeper layer.
So where do we go next in this search? How do we push these limits further?
Well, on the energy frontier, future, more powerful particle colliders could directly probe higher energy scales, searching for contact interactions or heavier excited electrons.
Higher Q², higher lambda limits, higher mass reach.
Exactly. On the precision frontier, improving measurements of G2 and the EDM continues to be crucial. Even small improvements can significantly constrain new physics.
Pushing those indirect limits even further.
Right. And then there are searches for extremely rare processes, like decays that violate lepton flavor conservation, an electron turning into a muon, for example, which are forbidden in the standard model, but might occur if they're substructure. Even things like high-precision neutron physics can offer indirect probes. It's a multi-pronged attack.
So wrapping up, the electron status seems secure for now.
For now, yes. Based on decades of incredibly careful and diverse experiments, the electron stands firm as an elementary particle, a true cornerstone of our current understanding.
Science never really stops asking what if, does it? The drive to understand reality at its most fundamental level just keeps pushing us.
Absolutely. We have to keep looking, keep testing, keep refining our measurements. Well, the electron looks fundamental today, down to 10 Curie meters or so. Who knows what reality looks like at 10 Curie meters or at the Planck scale?
It leaves you wondering, doesn't it? What secrets might this seemingly simple particle still hold? Could our bedrock reality be built on something even stranger?
That's the question that keeps physicists exploring. The ultimate nature of reality at the smallest scales is still very much an open book, waiting for the next chapter to be written.
A fascinating place to leave it. Thanks for taking this deep dive with us today.